Okay, welcome back. So in this lesson, we'll look at what the inverse Laplace transform is and how it's useful to take any order differential equation and re-express it in terms of an algebraic equation that we can solve and then apply the inverse Laplace transform to figure out a general solution. So it's going to be very exciting in the next couple of videos, but for now, let's get started on um, looking at how the inverse Laplace transform could be applied in some scenarios. So here's an example, and then going over the inverse Laplace transform. It's a function, okay? It's a function such that the inverse Laplace transform of f of s, capital F of s, is equal to um, lowercase f of t. Okay, so and one thing to point out here is that the inverse Laplace transform of capital F of s is also a linear function, right? Okay, so we have the quantities of b for linearity satisfied for the inverse Laplace transform, right? So plus of f plus of g, and then this condition here as well. So if c is a constant, and I'll leave that for you as an exercise to show this, okay? And you're just going to use the fact that capital F and capital G are just Laplace transforms of um, of little f of t and then g of t, okay? And then just use the fact that the Laplace transform function is a linear function, and that will lead you to the conclusions here, right? So I'll let you work on those for yourself. But the most important thing is how this is involved in an example like uh, this initial value problem. Okay, so we want to solve the initial value problem, y double prime of t minus y prime of t equals to negative t. Okay. And we know that if t is 0, y of 0 is 0. And if t is 0, y prime of 0 is 1. And then just to inform yourselves, I hope you have this table um, written down or glued to your brains, because it will be useful in the next couple videos from now. So hopefully you wrote those down. Okay, so we have the differential equation y prime minus y equals to negative t. So what we're going to do here is we're going to apply the Laplace transform first to both sides. Okay, so we're going to apply the Laplace transform to both sides. Okay, so what this looks like is we have the Laplace transform of y double prime minus the Laplace transform of y, okay, equals to the Laplace transform of t, or I should say minus the Laplace transform of t. Okay. Now we know the right-hand side. Actually, I'm going to get some more room here. So I'm going to write this equals over there. So we know the Laplace transform of t, right? It looks like this quantity, t to the n, right? And its corresponding Laplace transform is n factorial over s to the n plus 1 power. So the exponent on t is 1. So in this case, it would be 1 over s squared. And it's multiplied by negative 1. So the right-hand side will be negative 1 over s squared. Okay? So that was sort of easy part, I guess. Okay, so there's also another property of Laplace transforms of the derivatives of functions, right? The Laplace transform of the nth derivative of a function, right? So this was s to the n times the Laplace transform of y of t minus s to the n minus 1 times y of 0. Okay, minus y of 0 minus s to the n minus 2 times y prime of 0, and then minus all the way down to minus y to the n minus 1 power at 0. Okay, so that was the other property that I mentioned in the previous video on more properties on Laplace transforms. Um, so on the left-hand side, we have the Laplace transform of y double prime. So in that case, what that is going to look like is s squared times the Laplace transform of y of t. Okay. And then we'll have a minus s times y of 0. Okay. And then we will have a minus y prime at 0. Okay. So that would be the left-hand side. Okay, that will be the first term on the left-hand side. And then the Laplace transform of y, it's just the Laplace transform of y. We don't know what that is. But in the textbook, they notate these quantities. Let me highlight these more clearly. So these are the same term. So they denote this as capital Y of S. Okay. So that indicates a Laplace transform of y, okay, in terms of S. Okay, and then we know that y of 0 is 0, so this term would be 0. And we know that y prime of 0 is 1. So the left-hand side is just s squared times a function in S minus a function in S equals to negative 1 over S squared. Okay? Negative 1 over S squared. So if I erase this here, okay. So now the next step here is to solve, Jesus Christ. Okay, come on now. Work with me. All right. So the next step is to solve for this capital Y of S. Okay. So now we have S squared minus 1. So we factor the terms that have the capital Y function. Okay. And then minus 1. This equals to negative 1 over S squared, right? Okay. So now we'll have S squared minus 1 times capital Y of S equals to 1 minus 1 over S squared. And therefore, what we have here is that capital Y of S is equal to 1 minus 1 over S squared divided by S squared minus 1. Okay. All right. So if I just reduce this right-hand side a little bit more, we'll have this quantity, S squared minus 1 divided by S squared times S squared minus 1. Okay. S squared minus 1. Okay. So Now, from here, so so the next step is to apply the inverse Laplace transform to both sides of equation star. So this equation right here. Okay. And what's going to be the challenging part is not only looking up the Laplace transforms of the corresponding functions, but also you're going to use partial fractions decomposition. You thought that wasn't going to return, but it does. And it does hard. So from so to find the general solution in this case would be from this point forward, first to apply partial fractions decomposition, okay? And then two is use linearity for the inverse Laplace transform of capital F of S, okay? So it will be best if I review a bit on partial fractions decomposition, okay? You might have seen this in Calc 2, maybe. But there's going to be cases where we have either different linear factors, okay? In this example, if we factor out this right-hand side, the denominator of this right-hand side, what we will get is, if I erase this, okay, so capital Y of S, right, this is S squared minus 1 over S squared over S plus 1 times S minus 1. And this is equal to, well, the numerator by difference of squares, S plus 1, S minus 1 over S squared over S plus 1, S minus 1. This one's easy. Okay. I was freaking out for a second. So these cancel, and you'll get this function as the function in S. And what we're going to do is apply the inverse Laplace transform of y of S to get a function in T, and that will be our general solution. All right. So now, okay, so we have y of S is equal to 1 over S squared. Now, what we're going to do is take the inverse Laplace transform. Inverse Laplace transform of these quantities. So we'll get a function in T, little y of T, and this would equal to, well, we know that this is how we would compute the inverse Laplace transform of a function. So if I erase this stuff here, we know that 1 over S squared, it appears in some quantity that looks like this, right? Looks like that. We have an n factorial over S to the n plus 1 power. And it looks like that, right? So the inverse Laplace transform of that function would be just t, right? The n is 1 in this case. All right. And so that is what y of t equals to. All right, there's going to be plenty more examples where it's going to be not as easy as this example. And we're going to have to use some tricks in our sleeve, okay? So some math tricks. So Let's go over the partial fractions decomposition. So this is the first case. Okay, so I went over the linearity of the inverse Laplace transform. Okay. And then, so the first case is if your fraction, so A of S over Q of S. So if Q of S can be factored into a product of distinct linear factors like this, R1, R2 through Rn are not equal to each other. Okay, so Ri does not equal to Rj. For all I and j, that's equal to 1, 2, all the way up to n. Okay? So then the partial fractions decomposition will have this form, right? A1 over S minus R1, A2 over plus A2 over S minus R2, plus A3 over S minus R3, and all the way up to A sub n plus A sub n divided by S minus R sub n, okay? Where the A sub I coefficients are real numbers, all right? So there are ways to determine what the numbers A sub 1 through A sub n are equal to. But there's, you can do this by using linear algebra, or you can just straight up plug in different values for S and then figuring out what the coefficients A sub I would equal to. Okay, so I'll show you an example on how we do that. So here's one. So if I want to figure out the inverse Laplace transform of this quantity here, what we have to do is apply partial fractions decomposition. Okay. So we know that the denominator, right, it has three distinct factors: S equals 0, S equals 1, and S equals 6. Okay. There's no other numbers that are repeating. Okay. So 6s squared minus 13 times s plus 2 over s times s minus 1 times s minus 6 equals to capital A over s, okay, plus another constant over s minus 1 plus another constant over s minus 6, okay? So that's a partial fractions decomposition, okay? Next, what we want to do now is multiply both sides of this equation by the factors in the denominator. Okay, so in this case, so we want to multiply both sides by s times s minus 1 times s minus 6. Okay, so this is times s minus 1 times s minus 6. Okay, so we'll have an algebraic equation. So 6s squared minus 13s plus 2 is equal to a times, in this case, we'll have the s's cancel. So we'll have s minus 1 times s minus 6. Okay, this is so we don't have to deal with fractions, right? Okay, plus b times, so we'll have an s times s minus 6 that's left over, plus c, the s minus 6 factor cancels, and so we'll have an s times s minus 1. Okay, s minus 1. So let me erase this. Let me erase that. And so to figure out what the A, B, and the C number equals to, we can plug in various numbers for S for S and solve for the constants A, B, and C. Okay, so for example, if S is 0, that's a good choice. So if S is 0, the left-hand side of this equation, well, we will be left with 2. So 2 is equal to the B and the C terms will cancel, and you'll have A times -1 times -6. Okay, and so we'll have that 2 is equal to 6A, and that concludes that A is equal to 1/3. All right, A is equal to 1/3. Next, let's look at where S is equal to 1. That's pretty straightforward. So if S is 1, so the left-hand side, we will get 6 minus 13 plus 2, right? So yeah, so 8. Yeah, right. So -5. Okay. I just want to make sure I'm on track. Where the hell is it? Okay. Yeah, so I'll have a -5 on the left-hand side. And on the right-hand side, we know if S is 1, the first term and the last term are gone. And so we'll have B times, in this case, 1 times -5. And so B is 1. Okay, so B is 1. And one more. So if S is equal to 6, that's another good choice. So if S is 6, the left-hand side, so that would be 216 minus, so that's 18, 78 plus 2. And this would equal to, so the A and the B terms will cancel, and we'll have a C times 6 times 5. So -76, so 216 minus 76, that's 140, equals 230 times C. And so C is equal to 14/3. C is equal to 14/3. All right, so what this tells us is, okay, so we had our partial fractions decomposition form like this. S minus 1 times S minus 6. Okay, so what that implies is by partial fractions, we can write out that singleton fraction as so 1/3 over S plus 1 over S minus 1, and then plus 14/3 over s minus 6. Okay? For s minus 6. All right. So now what we need to do is take the inverse Laplace transform of this sums of fractions here, right? And so we'll have 1/3 times the inverse Laplace transform of 1 over s, and then plus the inverse Laplace transform of 1 over s minus 1. And so we'll have plus the, oh shoot, okay. So we'll have a plus 14/3 times the inverse Laplace transform of 1 over s minus 6, right? Okay. So the inverse Laplace transform of 1 over s, that is a constant, right? So, so that is a constant. So we'll have 1/3. The inverse Laplace transform of 1 over s minus 1, that will be e to the t. And then we'll have 14/3 times the exponent e to the 6t. And that is your answer. Oh, shoot. Okay, it's pretty straightforward. All right. So, okay. The other case is if we have a repeated linear factor in a rational function a of s over q of s, right? So if we have a rational function a over q of s, and they suppose that s minus r is a factor of q of s, and we know that s minus r to the m power is the highest power of the factor s minus r that divides q of s. Okay, so then the partial fractions decomposition of this quantity, right? This will be the following. Okay, so we have to take into account each successive power of the factor s minus r. Okay, so we'll have a sub 1 over s minus r plus a sub 2 over s minus r squared plus a cubed over s minus r cubed, and it continues all the way down to plus a sub m divided by s minus r to the m power. The a sub i terms are real numbers, okay? And then we just use either the same method for computing the coefficients a sub I as before, or we can use linear algebra, right? And apply row reduction. Okay, row reduction. If you have questions on how to do this in your calculator, please let me know, okay? But I'm going to assume that most of the viewers of this series is well familiar with the operations of a the TI-83 calculator, right? So with that, let's do another example. Okay, so we want to figure out the inverse Laplace transform of negative 2s squared minus 3s minus 2 divided by s times s plus 1 squared. Okay, so again, we want to apply partial fractions decomposition. So if you notice, the denominator here, okay, this time we have zeros at s equals 0. So, so we have the denominator where it's 0, where s is equal to 0 with multiplicity of 1, and we have that s is equal to negative 1. Well, let's see. Did I? Okay. Okay. Yeah, all right. So I had the right example. I had to double check. Okay, so yeah. So once again, if you look at the quantity in the denominator of this function here, which is given in the example, We want to look at where the denominator is 0. So we notice that can equal to 0, but it occurs once. So it has a multiplicity of 1. And also s can equal to -1, but it has an exponent of 2, right? So we can say that this has multiplicity of 2. So that's going to be important. S equals -1 is a repeated linear factor. So the partial fractions decomposition in this case will be, so minus 2s squared minus 3s minus 2 over s times s plus 1 squared. This equals to a over s that takes into account the s equals 0 root, plus b over s plus 1 that takes into account the first time that s plus 1 appears, plus c over s plus 1 squared. This right here is the appropriate partial fractions decomposition. Okay? And then the next step is to multiply both sides of this equation by the product of the factors in the denominator on the left-hand side. So it's just s times s plus 1 squared. So what we have here now is minus 2s squared minus 3s minus 2 is equal to a times s plus 1 squared plus b times s plus 1 plus c times s. Okay, so this is the equation that we will use to solve for the real numbers a, b, and then c. All right, so in this case, we can pick up different values for s. So if s equals 0, that's a good choice. Well, we know that the constants, the terms for b and c, they will cancel since s is 0. And on the left-hand side, we'll have minus 2 is equal to a times 1 squared. So this concludes that a is equal to -2. That's pretty easy. Right, so a is -2, right? Next, how about another value? When s equals -1. If s equals -1, we'll have we'll have -2 plus 3 minus 2. So the a term will go away, the b will die out, and we'll have a minus c that's left over. Okay, so -4 plus 3 is a -1. So c is equal to 1. Okay, so we know that c is 1. And so we know that c is 1. And lastly, you can also pick any other number to solve for the b term. Right? We also know that a is equal to -2 and c is 1. So if s is 1, that's a good number. So if s is 1, so we'll have on the left-hand side a -2, -3, so that's a -5. -2, so on the left-hand side is a -7. And on the right-hand side, so we'll have a 2a, and oh shoot, that's a 4a, since it's squared. So it's a 4a, excuse me. And then plus 2b, and then a plus c here. We know that a is -2 and c is 1. So what that means is this equation is -7 is equal to, so this is a -8 plus 2b, and then a plus 1, right? And we'll get that b is 0, right? We'll get that b is 0. if you add 8 and minus 1 on both sides, you'll get 0, which leads to saying that B is 0. Okay, so, all right. Now the brute force work is pretty much done. Let me erase this. So this was the partial fractions decomposition that we started with. And so the quantity we started off with, we can rewrite this as, so minus 2 over S. So the B is 0, so the B term will be non-existent. And then C is just plus 1 over S plus 1 squared. Okay, so that's what star that was given to us is equal to. Great. So now we're going to apply the inverse Laplace transform to these terms here. Okay, so this equals to minus 2 times the inverse Laplace transform of 1 over S, and then plus the inverse Laplace transform of 1 over S plus 1 squared. Okay, and so this equals to minus 2. And then the Laplace transform of 1 over S plus 1 squared. If you take a look at your table, it'll be T times e to the T. T times e to the T. That's your answer. Okay? So hopefully that made sense. The last case is going to be much more tough to articulate. That's okay. And it deals with irreducible quadratic factors. And I'm looking for the example that I did. So it's right here. Great. So if we look at the last case, this is if we have what is called an irreducible quadratic factor. That just means it's a quadratic trinomial that is not factorable. Okay. So for example, like this one. Okay. So this here is an example of an irreducible quadratic, right? So normally how you would factor this is you want to figure out two numbers where the product of those two numbers is equal to 5 and their sum equals to 2, right? This here is a problem since 5 is a prime number, right? It contains 1 and 5. So there's no way you can come up with a combination whose sum is 2 from those two numbers. So that's an example of an irreducible quadratic. But will that stop us from solving the equation, the differential equation? No. We're mathematicians, we prosper. So we are going to apply the complete the square method. All right. So complete the square method. All right. So if I go back to the other example I just wrote down, okay, so the idea is algebraically, what we want to do is look at the coefficient that is multiplied by x. So in this case, it's 2. So the b is 2. Next, what we want to do is divide the b number by 2. So in this case, it's 1. And then the next step is we square that number. Okay. And that number will belong to these spaces that are filled in here. So plus and minus here. And this was a +5. Okay, since it was 1, we put in 1 in this space and a 1 in this space. Notice here, it's a +1 here and a -1 here. So another way to re-express this quadratic, x squared plus 2x plus 5, is expressing the first 3 terms as a perfect square. So as you notice, x squared plus 2x plus 1 is a factorable quadratic, right? So in this case, it's x plus 1 squared, and then -4. Okay, so that's another way to express this quadratic, and it's this quadratic here. Okay, so that's a review on using the complete the square method, and it's very useful. But really, let's go over the method where we have an irreducible quadratic factor occurring in the denominator of the function a of s over q of s. So they represent the quadratic factor as s minus alpha squared plus beta squared. Okay. And then suppose that m is the highest power of s minus alpha squared plus beta squared that divides q of s. Okay, then the partial fractions decomposition will look like this. Okay. So notice here, right? We add in 2 constants for each fraction. One of them corresponds to the s term, and the other is just an ordinary constant term, right? So C1, C2, and all the way up through Cm are the respective coefficients on s, and then the D1, D2 through the Dm numbers are your constants. Okay, and so and then another way to write out this partial fractions decomposition, you can write out like this. Okay. But somehow I prefer to use this method. Okay. So, and this is where your knowledge or your knowledge of linear algebra should come into play. But I may post another video on how to do row reduction on your TI 83 or 84 or 85 calculators. But if you want to, just let me know in the comments. All right. So I'm going to bypass those instructions. I'm just going to use that to solve a particular example. So let's look at another example here. So figure out the inverse Laplace transform of, oh, I did this already. Okay. All right, so the function that it should be, so you want to figure out the inverse Laplace transform of 7s squared plus 23s plus 30 over s minus 2 times s squared plus 2s plus 5. Okay. So try to figure this out, because I'm going to solve it in 3, 2, now. All right. So now, once again, we need to apply partial fractions decomposition. But first, what we need to do is notice that in the factors of the denominator, s squared plus 2s plus 5 is an irreducible quadratic. I believe that was the last example I wrote down. So, um, so we know that it's an irreducible quadratic, and we can use the square method, right? And we figured out that this quadratic would be expressed as s plus 1 squared plus 4, okay? And I'm going to write this out as s plus 1 squared plus 2 squared, okay? So we have, so this quantity, will have a 7s squared plus 23s plus 30 over s minus 2 times this factor s plus 1 squared plus 2 squared. This would equal to a over s minus 2 plus bx plus c over s plus 1 squared plus 2 squared. Okay? That's a partial fractions decomposition. And if we multiply both sides of this equation by the product of the factors in the denominator on the left-hand side, so we'll have s minus 2 times s plus 1 squared plus 2 squared. Okay? This would equal to a times s plus 1 squared plus 4, and then plus bx plus c times s minus 2, and that would equal to 7s squared plus 23s plus 30. Okay, so we have this equation here. So we know that these are polynomials that are equal. So they're polynomials in terms of s, and they have to equal to each other, and they have the same degree, right? So what that means is, since polynomials are equal, that implies that the coefficients of the respective polynomials are equal. It's pretty cool. So we're going to use that to solve for the constants capital A, B, and C. All right. So, okay. Get ready for some really intense work. Okay. Okay. So on the left-hand side, so we'll have 7s squared plus 23s plus 30, and that will equal to a times s squared plus 2s plus 1 plus 4, and then plus, so, okay, this is s, sorry. So I have a bs squared minus 2bs plus c times s minus 2c. Okay. And so the right-hand side, this is a times s squared plus 2s plus 5 plus bs squared minus, I should say plus minus 2b plus c times s minus 2c. Okay, minus 2c. And so from this point, we're going to gather all of the S squared terms, the S terms, and then the constant terms on the right-hand side as three separate groups. So first, let's deal with the S squared terms. So for S squared, we have A and then B, and that's it. So A plus B. Okay. Next, we're going to deal with the S terms. And what that will lead us to get is 2A here. And this sum, 2B plus C. So this would be 2A minus 2B, and then plus C. And then plus the constants. The constants would be 5 times A minus 2C. So we'll have 5A minus 2C. And all of this, it has to equal to 7S squared plus 23S plus 30. Okay? So we're almost there. Okay? All right. So now we're going to use the fact that since the polynomials are equal in terms of S, the coefficients have to be equal. So therefore, therefore, we'll have a system of equations. Okay. So the S squared coefficients would mean that A plus B is equal to 7. A plus B equals 7. The S coefficients would lead us to say that 2A minus 2B plus C equals to 23. And finally, the constants. So that means 5A minus 2C is equal to 30. Okay, so let's see, I have partial fraction written down. Yeah, I do. Okay, so all right. Okay. So let me shit. All right. Let me just erase some of the stuff I don't need. Okay. So we can use algebra to solve for the coefficients A, B, and C since we have a system of linear equations, right? And so let me erase this too, because I'm going to need some room to work this out. So, okay. So we have this equation 1 and then 2 and then 3. Right, okay. So what if I want to use 1 and 2? So if I use equations 1 and 2, right, so I'll have A plus B equals 7, and then 2A minus 2B plus C equals to 23. What I'm going to do here in the first equation is multiply by 2. I meant 2 here. So what, shit. Okay, so what this would be is, so we'll have a 2a plus 2b plus 0 equals 7, and 2a minus 2b plus plus c. Oh, that's 14. Okay, so 23. This number here, it's 14. Okay, great. Now, if I add these terms together, I'll have an equation in terms of a and c. So we'll have 4a plus c is equal to 37. 37. And then also, if I use equations, okay, so if I use equations 1 and 3, let's see, I need to eliminate b. So, okay. 2 and 3. Okay. So, okay. Or maybe I can just do substitution. That's a lot easier. Yeah, there's no way I can do elimination here. So, yeah, I'll do substitution. Because if I solve for a in equation 1, so I'll have a is equal to 7 minus b, and then by equation 3, I'll have 5a is equal to 30 minus plus 2c, and then a is equal to 30. Oh, shoot. Six plus 2/5 c. Okay. All right. So and we know that okay. So okay. So um okay. The sky's getting dark. Okay. So 7 minus b. Okay. And then from 2. And I know that c is equal to 23. So I'll have a minus 2a plus 2b. And so c is equal to 7 minus b was a. So 23 minus 2 times 7 minus b It's 2 times b. And so c is equal to 23 plus 14b plus 2b. And so, oh, shoot. Okay. I gotta slow down. Okay. So that is so 23 minus 14. That will be a plus 4b. And so, okay. So I believe that is 9 plus 4b. And then just use the fact that a is equal to this quantity and c is equal to this quantity to solve for b in the third equation. So we'll have 5 times 7 minus b, and then minus 2 times 9 plus 4b equals 30. Okay, and so we'll have 35 minus 5b minus 18 minus 8b equals 30. Okay, so we'll have 17 minus 13b equals 30. Minus 17, that's 13. So b, okay. What we reduce down to is if we subtract both sides by 17, we'll get 13 on the left-hand side, and we'll get minus 13b equals 13, which leads that b is equal to 1. And from our equations, a is equal to 6, and then c is equal to 13. C is equal to 13. Sweet. So, hard part's done. Okay, let me erase this crap. So, the partial fractions decomposition, right, was a over s minus 2, and then plus bx plus c over s plus 1 squared plus 2 squared. And so this will correspond to saying 6 over s minus 2, and then plus s plus 13 over s plus 1 squared plus 2 squared. Okay, pretty sweet. And so we can reduce this down to 6 over s minus 2 plus s over s plus 1 squared plus 2 squared plus 13 over s plus 1 squared plus 2 squared. Okay, now the last piece is just take the inverse Laplace transform of these three quantities, right? So we're going to take the inverse Laplace transform of these guys. Okay, so the first term, okay, we know that this equals to sits over s minus 2. So if we go, if I look up on the table, so that would be 6 times, okay. 1 over s minus 2. So the t is 1. Oh, wait a minute. The t is, the n is 0. So, okay, yeah. So this would be 6 times e to the 2t will be the first term. And then plus the second inverse Laplace transform it'll be s over s plus 1 squared plus 2 squared, right? So, so in the Laplace transform, that will correspond to e to the at sine of bt. Okay, so the b is 2 and the a is -1. So, oh, wait a minute. Okay. Oh, hang on a second. Okay. Now this is interesting. Okay, so we have, so the second term is s over s plus 1 squared plus 2 squared. The Laplace transform of this quantity, right? Oh, I'm sorry, that's the wrong one. So I meant cosine. So cosine of bt. This is equal to s minus a over s minus a squared plus b squared. Okay. We don't have an s minus a term in here. So what we're going to have to do is do a little bit of a math hat trick. Okay. So we're going to take the inverse Laplace transform of s minus 1 plus 1 over s plus 1 squared plus 2 squared. Okay. So that's what we need to do. And we have this other term here too. So it'll be plus 13 times the inverse Laplace transform of 1 over s plus 1 squared plus 2 squared. Okay. All right. So okay, let me erase that. Oh, Jesus. All right. Okay. So what this turns out to be is so we have 6e to the 2t plus the inverse Laplace transform of s minus 1 over s minus 1 squared plus 2 squared. And then we have 2 of the same quantity. So, so I have plus 13 times 2, that's 26. So it'll be plus 26 times the inverse Laplace transform of 1 over s plus 1 squared plus 2 squared. Okay, so now we can say that this is equal to 6 times e to the 2t plus, so this quantity here, that would be e to the minus t times cosine of 2t plus 26. And this is what we need to compute for next. Now, we know that e to the at sine bt equals to b over s minus a squared plus b squared, right? And so this would be equal to 26. So we need to add in a 2 in here, right? So we need to divide by 2 and then take the inverse Laplace transform of 2 over s plus 1 squared plus 2 squared. And so the conclusion here is we're just about done. Thank you, everyone, for sticking out with me, even though it's bedtime. Okay, so let me erase this. Jesus. Come on. Okay, so this inverse Laplace transform is 6 times e to the 2t plus e to the minus t times cosine of 2t plus 13 times e to the minus t times sine of 2t. And that's your answer. Okay, I'm pretty tired at this point. So if you enjoyed this, that's awesome. If you have questions, please let me know. And I will go over how Laplace transforms are useful in solving an nth order differential equation. So take care, everyone, and I'll see you next time.